Hi everyone, this is Quentin from Group MB3 for the spring semester of 2017 for ECE 4960. Today I'll talk to you about our floating magnetic bearing design. I'll start off by introducing the system design requirements. The main and most important requirement was that the system needed to be able to float a desired height beneath the steel plate. Floating in this case meant that the system should move with essentially zero friction. The system also needed to lock to the plate and switch back and forth between lock and float mode when desired. The distance between the magnets and plate needed to be adjustable, and the whole system needed to be controlled with a remote control. For our project, we decided to use a Bluetooth remote control done through a phone application. Finally, the project needed to be powered using an onboard power supply, which in this case was a battery. In order to get the system floating, our team needed to gather several pieces of data to perform mathematical analysis for the system. One test dropped a magnet from various heights beneath the steel plate by lowering the current each time. This data gave our team our linearization current, which is the current needed to have the system floating at our desired height, which was 0.75 millimeters. Another test gathered data from our distance sensors, which output a varying voltage depending on the distance from a certain object. After getting this data and selecting our desired height, our team used MATLAB and Simulink to create a control system for our bearing. This control system reads in voltages from the sensors and adjusts the current in each magnet to keep the bearing floating at the selected height. Here is the control loop we used for the magnetic bearing. In this loop, raw voltage data is read in and converted to a distance using our curves taken from our sensor tests. This is sent through a controller we designed using a root locus analysis and is outputted as a current. This is then converted into a duty cycle value for a PWM signal, which is sent to each magnet. The control system also includes a block which allows for Bluetooth control and changes the reference distance, which is the floating height. Next, I'll go over some of the more important pieces of hardware that were used. The TIVA microcontroller was used for all computation in the system and read in voltages from the distance sensor. The TIVA also sent the PWM signals to each magnet. The QRE1113 distance sensor was used to give specific output voltages for a given distance. This output was read directly into the TIVA. Each sensor was mounted directly next to each magnet and placed within its optimal sensing range. The last hardware component I'll talk about is the HC05 Bluetooth transceiver. The HC05 connects to smartphones via Bluetooth and allows for control through a phone application. The application switches between locked and float mode and also changes the floating height of the bearing. Here's a picture of the phone application that's available for use on Android devices. Some of the buttons on the application are turn on, disconnect, get visible, and list devices, which are both used for Bluetooth connection, lock, off, and the buttons 1, 2, and 3. Button 1 stands for 0.5 millimeters away from the plate, button 2 stands for 0.7 millimeters away from the plate, and button 3 stands for 0.9 millimeters away from the plate. All three are used to change heights while testing out the bearing.